Hey everyone, my name is Matt Kosovec, CEO and co-founder of DataForge, and today we're going to be talking about the object model within the DataForge framework. This is part 2 of a series of videos to help introduce the concepts of the DataForge framework. And if you haven't already seen part 1 of this video, I highly encourage you to do so. It'll help you have a lot of the context, and we're going to start this video off where we ended the last one about the column pure and row pure structures that DataForge leverages in order to rethink how data engineers work with their SQL, how they build their data platforms, and how DataForge helps organizations grow and extend their code base over time. So with that, let's jump into the slides and start talking about where we left off last time. So we talked about column pure and row pure functions, and just as a quick review, column pure functions are going to be transformations that add columns to the existing tables or add columns to the existing logic without changing the number of rows in the data set. Row pure functions, on the other hand, are going to be transformations that change the number of rows but do not change the number of columns. And the reason why we break things down into these two groups and we don't intermix them is because there are a tremendous number of benefits on the column pure side to work in a purely declarative functional pattern. And there are a lot of things in the computer science world that have been developed over the past couple of decades that show that keeping things in the column pure world will allow us to introduce a lot of these powerful principles and best practices and encourage things such as code reuse if we keep as much of our logic in the column pure side of the house as possible. So let's talk about how we've taken these ideas and we've built an entire class and object model around restructuring your data transformation logic, what those objects are, and how to leverage them in order to build a data platform. Starting with the most foundational object in the DataForge model, we're going to look at a rule. DataForge rules are roughly equivalent to SQL expressions. For those of you who are unfamiliar with a SQL expression and how they differ from a SQL query, a SQL expression is a smaller component of that query. So it can be a single line of a select statement, it can be what happens after a where clause or after an on in the join statement, and it is a set of symbols and operators that evaluate to a single data value, meaning for any set of input columns, it operates and results in a single output column. And going back to our part 1 of our blog series, that definition looks a lot like what we defined a column pure function to be. These column pure functions in the rules allow you to do transformations and a lot of complex operations, data quality rules, so on and so forth. And looking at the different syntaxes here within MS SQL, this is how they defined the syntax. Again, it's a pseudocode to help you type in a single expression. Again, these can then be plugged into a query. Whereas in DataForge, we break out the expression into its own separate statement, its own separate object within the context of a rule. So a rule has two components, an expression. You can see this pseudocode here. We'll come back to this in the following slides. But here we're doing a simple operation of extended price minus tax minus discount times 100. And the result of that expression is going to be stored in a variable or in a resulting column called net price int. So very simple, straightforward, easy to understand syntax that allows you to segment out and operate on the data, column by column by defining these SQL expressions. Next up, we're going to take a look at where this data is coming from. So obviously we have the transformation code here. Now we got to figure out what this means and where these columns are sourced from within the object model. Within the rule syntax, we referenced a number of columns. When we're referencing those columns, they need to come from somewhere. Data transformation, by definition, is taking existing columns that may live in an existing system, in a file, in an Excel sheet, and then transforming them into another set of columns. Within the DataForge object model, we're next going to look at raw attributes. Raw attributes are going to be static columns that live or were created from outside of DataForge's transformation model. So if rules are creating new columns by transforming existing ones, raw attributes are going to be the raw columns, the raw attributes that are coming into the system from somewhere else. Looking at the syntax, very straightforward. On the left here, we have SQL DML. On the right here, we have the DataForge raw attribute YAML syntax. Within DataForge, we do require you to define, or we require the definition of all of the raw attributes, such that we can ensure type safety, we can infer lineage, and we have a lot of other features that are tied to making sure that these columns are well structured and defined within the actual object model, and everything points to each other. Speaking of pointing to each other, here's a quick entity relationship diagram of how these two introductory objects work together. A raw attribute can be used in many rules. A rule can use many raw attributes, and a rule can use many rules in its definition, or be used by other rules in their definitions. So again, very powerful set and flexible set of capabilities that ultimately results in defining a set of raw attributes and then building a bunch of rules based off of those raw attributes to create your transformation pipeline. The last thing I'll mention is in our cloud product, the definition of these raw attributes is automated. There's also a lot of features around schema evolution and other capabilities so that the static definition of these raw attributes don't hold you back in a production environment. Now that we've defined rules and raw attributes, we're next going to take a look at their parent object, which is a source. A source is a logical construct to help organize rules and raw attributes and help us reference them when we're working with more complex pipelines and doing cross-source joins, so on and so forth. Taking a quick peek at the three new things we've added. So of course we have raw attributes and rules that we're putting within the context of a source. We have a source table and a target table. The source table is going to be where the raw attributes are coming from. What table are we starting with to augment and add these rules to? The target table is going to be where are we saving those results to. So, and then lastly, source name is going to be a developer-friendly alias for referencing everything within this source, within this object. You can see the same syntax we already reviewed for raw attributes. Rules here, you can see some more examples of rules, right? Some more expressions with a case statement as well as a concat function here. With the different results. And just to clarify, we covered this in the part 1 of blog, but all rules, all column pure functions by definition are in the context of an existing schema or an existing set of rows. So it's very important for us to say, all right, these rules, they're going to be defined on an existing table or on this set of raw attributes. And we're not going to be changing the number of rows. We're just going to be adding these columns, these rules with these names to the existing data set. With the jumping over to the entity relationship diagram or the class diagram here, all rules and raw attributes belong to exactly one source. There's some advanced functionality with something called templates that allow you to write logic that can be applied across multiple sources, but those templates are ultimately materialized into actual rules that live within a source. So again, all rules, all raw attributes always are tied to a specific source, which then allows us to work with the data and reference the exact column from the exact table that we want to use within a rule, within an expression here. Rounding up the syntax, you see this column, this bracket. Anytime you see a bracket, that is a reference to a source within the DataForge framework. Anytime you see a this, it's referencing the source that is contained in the file. So anytime you see this, it's actually an alias for a tpch_line item. If we were writing a function or a rule that wanted to reference tpch line item in any other source, we would have to use the entire tpch_line item reference for that source. With the transformation code defined in rules, where it's coming from defined with raw attributes, and the table container or the parent object defined as a source, we're now ready to talk about connecting different tables, connecting different elements together. And when we're doing a connection between sources or a reference across sources, we're going to be talking about a relation. And a relation, as defined, is essentially a join with cardinality. So it's a SQL join that has the, is it a many to many? Is it a one to many? Between those two tables or those two sources when you're working with that join condition. The important part with DataForge relations and how they differ from SQL statements and join conditions is that they are universal to all sources and all rules within the object model. So in contrast to a single statement that has the join buried within the statement, and that statement then, the on condition of that join cannot be reused across different select statements, across different where clauses, across different queries you may want to run. DataForge breaks out that connection, that join, and puts it into its own object, and then makes it referenceable across the whole framework, across every rule you're writing, across every source within the system. And so the result of that is a new data model that is developed focused on ETL, or focused on your transformation code, that is separate from the source system model or the source system database, foreign keys, and your target data model, which, whether you're doing a one big table or a Kimball star schema, or just building features for an ML model, they have their own specific joins and target data models that are useful for their end use case. What we're building with DataForge and the DataForge relations is a combined transform model that is focused on allowing for code reuse, a common set of connections between tables that then all engineers, all developers, all team members can reference and collaborate on to prevent code duplication, copy paste, and a proliferation of different pipelines or different types of logic within the overall data platform to help engineers manage and operate these transforms at scale. So thinking, in the traditional fashion is I have my pipeline and I need to think about things from source to target. I'm building a point-to-point solution. What joins do I need to do in order to kind of take the data from source to target? With the DataForge mentality, you should be thinking about what are all of the global connections between the different tables within all systems that are being ingested and transformed by this platform. And how can I develop a model just by defining connections between those different tables to allow for the most flexible and powerful set of operations to be transformed against that model and result in a wide variety of different target system target models. Not just focused, for example, on reporting, but maybe focused on third-party integrations, APIs, event streams. All of these different things can be derived from this combined transform model or materialized from this combined transform model. With all that said, taking a quick look at the YAML syntax for relations is much more simple than the bigger concepts around the combined transform model. Looking at the syntax, we have two sources, as all relations are using two sources within their definition. In this case, we have line item and orders. On the left-hand side, we're always going to be referencing this is going to be the one on the left. Related is always going to be the one on the right. And the reason we talk about this is because of this cardinality statement. This is always going to be, again, the thing to start with. So if we're going to be referencing a line item, that is going to be the many. Orders is going to be the one. This expression can be any Boolean SQL expression, again, aka any type of on condition, join on condition. That is legal within normal SQL is legal within this expression. So this can obviously get pretty complex. The only thing I'll mention is that looking at this ERD, you can see that a relation can use many rules, a relation can use many raw attributes within the context of it. Every relation always uses exactly two sources. But the important part here is that because you can use rules within the definition of a relation, you don't need to include all the complex logic within this exact expression statement. The best practice is going to be to actually do all of your pre-calculations, your combinations or concatenations of different columns within the rule definitions, and then simply reference that rule within this expression, right? So one of the overarching best practices is to try to keep each object or each rule, each relation, each statement relatively simple so that it's easier and more straightforward to debug or for someone else to come in and branch off from that logic at the point of that transformation. All right, so we've covered a lot of different material. We've covered sources, rules, relations, raw attributes. We have all these different objects. Let's think through an example to start bringing it together. So here we have a sample project data model. We have our kind of transactional level table here, TPCH line item, and then we have some dimensional attributes or some extra lookup tables that are connected to this via some joins and some natural keys between primary keys and foreign keys between these tables, right? So we have line items connected to orders between a many to one with order key, and then orders is a many to one to customer. And then we have item can also go up to this part supplier table. This one is through a compound key. And so we're going to go through a couple examples here and talk about how you can leverage this framework to build some logic within the platform. One thing to note is when we are moving between tables and we're moving through a relation from one table to the other, we call it a traversal, right? So again, this is just a different name. The important thing about a traversal is when you're leveraging a relation, you're going to always be using that relation in the context of a rule, and that rule is always going to be attached to a source. So thinking about it in this example, right, we have maybe line item and orders, and we're going to go through it in a more visual way in the next page. But if we're moving from line item to orders, we're going to be traversing the relation, right, here that is set up between order, it is set up on order key between these two tables. And so you could also then jump an additional layer over to customer. You would then be traversing orders to customer across the relation that exists here between the two. So again, when we're talking about traversals, we're always starting with a table, almost like a left join concept. And we're then going to be moving across these relations that have this cardinality in order to go and get data or build logic within our transformation model. Let's look at how to use traversals to combine data between two tables, and specifically the logic and how to maintain column purity when connecting two tables or when traversing through relations. The most important thing to note is when moving from many to one through a cardinality, again, all rules start on a source and then through a traversal can move to another source via that relation. When that cardinality is from many to one, you can do that as many times as you want. You can jump to another source, you can connect to another source that's connected to that source, so on and so forth, as many times as you like without breaking column purity. So with the TPCH line items example here, whenever you're moving from the many side to the one, hey, I'd like to use a column within TPCH orders to do some type of calculation within a rule defined within TPCH line item, I can do that freely. I'm able to basically reference this data without having to worry about breaking column purity. However, if I were on TPCH orders and I wanted to reference a column within TPCH line item, that is illegal within the DataForge framework because it would break column purity. It would create a new row through the join condition or multiple rows for each row with it through that join, and it would break column purity. So you would think that would be a very limiting factor within, hey, I have to oftentimes reference data that is somewhere else in the system, and it's not always a clean many to one cardinality between those two tables. How would I work through that within the DataForge framework? The most common approach is to actually do an aggregate to transform that one to many, again, illegal transformation or illegal reference to a one-to-one. And you can do that by running an aggregate function over that traversal or over that join. So let's take a look at example 2 here. So here we have orders and line item, exact two same sources here. But now we want to, again, start at orders, and we want to then reference an element within TPCH line item. What we're going to first do is run a group by or an aggregate by over the columns that are included within the relation expression, right? So the join condition between these two ultimately becomes the group by fields within an aggregate function that is run over this. AKA what we're doing is converting this relation from a many to one to a one to one. By running a group by and aggregating over all the fields within the join condition, we are translating it to a one to one. And you can see, hey, here's an example. Maybe we run sum over sum of the line total, grouped by the orders ID. Right? If we group by orders ID, we now have an aggregate table that is at the orders ID level. And because it's at the orders ID level, that is the primary key of orders, we now have a one-to-one relation that we can traverse freely. So again, many-to-one or one-to-one, you can traverse freely. One-to-many, you have to either aggregate or convert to one-to-one or find other solutions to reference that data without breaking the column purity of the function and work with the then resulting elements within that logic. So with that long-winded explanation, thankfully the syntax to do this aggregate or this conversion from a one-to-many into a one-to-one within DataForge is really simple. So what we can see up top here is something that would fail during compilation. If we're on the TPCH orders source and we then try to reference the extended price, which is a field on TPCH line item directly, it would fail during compilation. It would give you an error saying you have to wrap this in an aggregate function in order to reference the column through this traversal. However, the correct syntax here, if we add the sum function around the TPCH line item extended price, this will compile correctly and will infer that you're looking to group by the join condition of which these two sources are connected via relation. All right, so even though this says first half summary, even though logically we're only through half of the objects we're going to be working with, when you're working in DataForge, 80%, oftentimes 90% of the time and focus and logic you're going to be developing is hopefully going to be in that column pure world of sources, rules, relations, and that combined transform model. I do want to take a step back and look at comparing what you do in DataForge to what you'd be building in other technologies, such as data frames or DBT models or other solutions which work at this table level rather than working in our object model, which we've discussed so far. So when you're working in those solutions, it's up to the developer to decide essentially how to group their transformations together. We have, this one is focused on the left-hand side more on code reuse. Hey, let's bundle up some logic so that we can reuse it maybe as part of a different transformation later on. Here, they may be focused on performance and storage optimization. Hey, we don't need these intermediary tables. Let's do it all in one shot and just produce the result. This obviously is less reusable, but hey, there are benefits. So one developer may decide this way, another developer may decide to take this path. With DataForge, there's no decision-making process on the number of stages or how the code reuse is structured. With our platform, everyone's following the same paradigm, everyone is building within the same object model, and it looks like this with this first half of the platform. Here we have sources that are then taking raw attributes and they're adding rules, right? So the gray here is going to represent the raw attributes that are passed through as part of the transformation, and then green are going to be the rules. And again, remember, these rules, they can be columns that exist on table A. They can be a combination of table A and B. They can be a calculation of A and B that is then used in a new relation for a third column or table C, so on and so forth. So it's not just about kind of moving data logically from left to right. You're able to move data also through the combined transform model between sources as part of this process as well. So again, even though it looks relatively simple, which is a good thing, it's a very powerful pattern where you can do a lot of different calculations and combinations of different data elements from many different sources within this structure. All right, and just as a preview, jumping into the final section here, we're going to be talking about outputs. Outputs are going to be how you do your row pure transformations. So we've spent a ton of time on column pure transformations and I've been kind of preaching about all the benefits that go into it. However, obviously, sometimes you do need to change the number of rows, especially if you need to create a new grain of data that doesn't exist naturally within the source tables that you're working with. When that happens, or you just want to do some aliasing, or in our cloud product, you want to publish to an external location with reverse ETL or any other solution, you do that with outputs. So we're going to be talking through what outputs are and what their uses are as part of this next section. And again, I just wanted to provide this as an apples to apples with that comparison that we talked about with DBT or table level operations, because before we had kind of two tables to two tables. Here now we have two tables going to one table in the similar fashion. All right, let's jump into it. All right, starting at the end. So here we're going to be moving from kind of right to left, working our way back towards sources as we think through the logic. So let's start with the end in mind. Here we have output columns, very similar to raw attributes. This is going to be, what does the target table look like? We're going to be defining that within our structure so that DataForge can manage that target table and hook it up to the upstream logic appropriately. Very simple syntax. What's the target name? What's the data type? That's it. Yeah. And so again, our column syntax here should be, again, very much like the SQL DDL, but we put it in a different object because logically in our system, it's a target versus it just being a normal table. Moving one step backwards from the target columns, let's look at mappings. Mappings are relatively simple. They do one of two things. They're either an aliasing from a rule or raw attribute within a source to a output column. Again, the output columns we just talked about are where the data is finally landing. And on the left-hand side here, this is the name. This is a source column, which is a raw attribute or rule. And on the right-hand side are going to be those output columns. So very straightforward syntax, from and to. The more complex one is going to be aggregates, where you can do group bys. It's very important to note that you should only be doing these group bys if the data, the level or grain of data does not exist naturally within a source. So the most common reason for this is if you're maybe feeding an ML model that is predicting the future by day. Every day it's going to have maybe a revenue forecast. To train that model, you need to feed it data that is aggregated by day. And in your source system, you may not have a day table. More often than not, it's just an aggregation. So here we're going to see a sum of the kind of rule total, revenue less tax. We're going to group by order, date, and name, and then we're going to publish the result of those calculations to order name, order date, revenue less tax. And this result will be at the order name, order date grain. Again, one thing to round up and note is you cannot do any SQL expressions here, right? So typically, in the rules and in the rules definitions, you have a ton of flexibility to do all kinds of different calculations. There are no scalar calculations or otherwise available to be done at this layer. You can only do those in rules. And likewise, those rules, you cannot do aggregations to new grains of data. You have to work with the grains of data that are natural within the source tables that you're working with. And only if and only when you need to aggregate at hopefully the last minute to a target grain of data, you do that within this aggregate mapping. So quick look at the ERD down at the bottom here. Every column map can only use one raw attribute or one rule. You can't combine columns together as part of a column map. And every column map is targeting exactly one output column. There is no ability to have a column map be pushed to multiple output columns. Now that we've defined where we're pushing the data to and the mappings of where the data is coming from, we have a couple extra objects or features within this second half of the object model to help developers round out all the different components of SQL. So a channel, starting with the top part here, is going to be what source to get the data from. We'll talk about a bit later about how this is leveraged to help with a SQL union statement. But in short, I referenced previously that mappings, right? You're getting the column from a source. You're getting the column from a rule or raw attribute that lives within a source. A channel is simply the definition within the context of that target table, that target output of where that data is coming from. AKA, it is a source to output junction object, right? You can have many channels within a single output to help, again, do different types of calculations. So again, syntax here, very simple. So again, all mappings are part of a channel and all channels are part of an output. Lastly, to round out the different types of operations in the row pure side of the house, we have a filter. So we talked about aggregates and how to do group bys. That's when you want to take many rows and reduce them to a smaller number of rows. Via aggregation, the other way to take many rows and reduce them to a smaller number of rows is via filter. So very simple. We add a filter clause here. It's part of the channel. It is done at the channel level, and it's always going to be referencing this. It's always going to be referencing the source and how to filter that source specifically. So it's, again, encouraging developers to think about both aggregates and filters as the final step of the pipeline. versus interspersing those different filters and aggregations throughout the pipeline, throughout the number of stages that you may have custom designed for various reasons. Here, we highly encourage or even prevent developers from interspersing those filters, and we require them to put them all in one place to help organize and help teams collaborate and build efficiently and promote code reuse throughout the entire platform. Similar to sources, which we covered in the first half as the parent object for column pure functions, outputs are the parent object for the mostly row pure parent objects or classes that we've discussed so far. So looking at them, we have the output columns. These are going to be where the data is being pushed to. It's kind of your final destination, final materialization of that combined transform model. And then we have channels, and that's a plural, channels. You can have multiple channels for a single output. And as discussed, channels contain mappings. Mappings are going to be, again, whether they're those simple mappings that are just aliasing from a rule or a raw attribute that exists within a source, or it could be an aggregate mapping. And again, these channels can also have filters to reduce the number of rows that are within that specific source. With all of these things together, you can do a number of powerful patterns to do the SQL transformations that are not part of the typical select statement, such as first one we're going to talk about is a union all. So again, if you want to stack, two different tables on top of each other with common columns, you can do that, such as in this example, via two channels on a single output, right? So you're defining two mappings, one from TPCH line item and one for part supplier in this example. However, the target columns are shared, right? So you're taking the same columns, different columns from the sources. However, you're mapping them to the same columns, which means you will do a union all operation logically as the final target table. And again, here you can mix and match this combination of multiple channels with the other two types of mappings, ones that include filters, and of course the ones that are aggregate mappings. The other nice thing from a syntax perspective is you don't need to include all the columns that are in that mapping. You can just include the ones that are relevant to the specific source that you're mapping to, and every other column that is unmapped will be null. Again, nice thing, union alls, you need to kind of null out columns and define everything. It becomes very verbose. Our syntax allows you to be more flexible with that. Two final pieces, just to note here, are that we have this concept called a loopback. This is when you hit a situation where you can't stuff all the logic within just one round of sources and one round of outputs, and you need to actually run it through multiple times or hopefully at the very most twice. And that becomes a very powerful pattern, especially if you want to do third-party integrations. So for the most part, you can actually fit the large majority of your transformations through one round of sources and one set of outputs. However, for example, if you want to do integrations with a machine learning model or other external lookups or other external situations where you can't bring that data into the platform that DataForge is operating on top of, and you need to run a RESTful API or some other more complex non-SQL operation, that can be done with this loopback pattern. And we call it a loopback because you're essentially hooking up an output to an extra step and then hooking up that extra step to a source. So you're kind of taking it out and then bringing that data back in as a new source. It becomes a very powerful pattern. We have a whole SDK that allows you to write custom Python, Scala, Java functions, R functions to do these more complex calculations for things that don't necessarily fit within SQL. So just putting that out there in our cloud product, you have this very powerful framework. If during this example or walkthrough of objects, you were thinking about, well, what about this? Well, what about that? Again, most of it can actually fit in the framework. And again, we encourage you guys to reach out to us and engage in the community to ask how to do that. But there are situations that don't. And when they don't, we have this very powerful pattern to allow you to write your own custom logic. The last piece here is going to be the output aggregation. So again, it's novice developers to using the DataForge framework oftentimes will create all kinds of aggregations at the output level because that's how they're used to thinking about data transformation. You should only be creating output aggregations when the grain of data doesn't exist naturally within a source, right? So if, for example, we had the orders and the line item, oftentimes people will think, well, I have a group by statement that says, I want to take the line items and group by these different elements or these different attributes to get it up to this higher level of grain. And then and then if you look at it more closely though, you realize, oh, actually that's actually at the order ID level. And because it's at the order ID level, you then no longer need to do that group by. You can just use the orders table or source naturally and create rules to do that, again, that more complex calculation of aggregations within a column pure function versus doing it at this output level. So again, you want to avoid aggregations. You want to avoid doing any logic at the output stage as much as you can. You want to push as much of it as you can to that column pure side of the house. So with the output, we've now covered the full framework or introductory framework for DataForge, specifically related to DataForge Core, which is our open source solution. I highly encourage you to go check us out on GitHub. But just a quick review of combining it all together. We have sources and outputs as our main parent objects. Channels connect them together. Within sources, we have raw attributes and rules, and then of course relations, which connect multiple different sources together. And then finally, at the more granular level, sources and outputs are connected to column maps, which then target specific output columns. With this overall model, you have everything you need in order to do the majority of data transformations and do it without a multi-stage design and in a solution pattern that allows you to add more rules, add more calculations, add more transformations to it over time without the need for refactoring or rethinking or replatforming. That's it for the DataForge Core side of the house. Our cloud product is much more broad. It's got a lot of powerful features such as processing history, lineage, cloud resource management. So today DataForge Cloud supports Databricks. There's a lot of details around cluster management and simplifying the use of jobs clusters, and many, many more features such as templates and cloning, which we talked about, that allow you to define a single bit of logic and apply it to multiple rules, and so on and so forth. With DataForge Cloud, it's a full enterprise production-ready solution that has a lot of bells and whistles to help your team manage it at scale, versus DataForge Core is focused on smaller teams or more simple overall solutions that don't require all the robustness and capabilities here. Thank you so much for watching the video. Appreciate your patience. This one was a long one, and we only covered the tip of the iceberg with the DataForge object model. Please check us out again on all the different social media platforms, YouTube, LinkedIn, so on and so forth. And please give us a star on GitHub. It really helps us grow, and it really helps us understand what the community engagement is. We also have a Slack channel. Please connect with us there. All these links are going to be in the description below. Thank you very much.